That's great. So yes, we can start, and it's a pleasure to introduce Rachel Armstrong from the University of Newcastle in the UK.
Thank
you. And the talk is, the topic sounds very interesting. It's on experimental architecture and embodied intelligence, and the floor is all yours.
Well, thank you, and thank you so much for this invitation. I can see an amazing screen of a diverse audience all around the world ahead of me. So you're obviously at all different times of the day, and I will try and keep the pace and the energy up, and tell you about my work. So the reason I'm interested in embodied intelligence is, I guess, from an architectural perspective. I'm interested in how materials appear to make decisions. Now, when we generally think about intelligence, we think about human intelligence and the way that humans think. And obviously, there's a long practice in studying human intelligence. So we have rather a particular worldview as to what this is. And I kind of want to put this to one side and saying that the thing that interests me in the field of embodied intelligence is the actual coupling between matter and information. Because I think particularly in the digital age, this is a very important area. So even when we have something like an explosion of technologies like 3D printing, we're still effectively working with matter that's fairly obedient. And so, with the kind of interest in soft robotics, like the presentation that we've seen, where non-linear materials are being incorporated into computing and engineering solutions, I think it's worth revisiting, the diversity of potential solutions between matter and information. And I'm going to do this from an architectural platform. So again, just for me to open up a conversation about possibilities, to actually create a graphical interface. So I would say that the work that I've been doing has a visualization quality. I'm not going to claim that it is an extremely functional tool in that it solves any particular grand challenge, but I think that it does provide us with some insights into a range of possibilities within the material realm that perhaps have applications that could lead to different kinds of innovation, and specifically in the built environment. I'm interested in how the buildings around us can be more lifelike. Can we make an origins of lifestyle transition in the built environment so that when we're thinking about more nature-like impacts, that we actually, rather than represent natural phenomena, but can actually engage with the physical processes through the diversity of material solutions that nature itself taps into, and from a very, very basic perspective, how can we intelligently engage in a material dialogue that helps us, collectively, I would say as a community of engineers, scientists, designers, work in ways that give us more environmental effects. And so I would say that the language that we're using in the particular system that I'm about to talk about is a language of metabolism based in physics and chemistry. And so to build these systems, I'm interested in how we may choreograph the networks of biochemical reactions that constitute a metabolism. And these are the chemical conversations that link the living world to nature and enable life to make the most of its local resources. And it's this scope for natural and unconventional and morphological computing to work with embodied intelligences that particularly interests me. And again, I think this might help us move away from architectures that inevitably damage ecological systems, and instead construct infrastructures of interconnected systems and prototypes that work symbiotically with and even enhance our environment. Essentially, my field is one of experimental architecture. So what does that actually mean? Well, it's a research practice that's been around since the 1970s. The term itself was coined by Peter Cook, and he used it to critique, let's call, modern architecture. And as you probably know, modern architecture has been characterized by Le Corbusier, a famous French architect, as being machines for living in. But can we think of architectures as being ecologies for living in, or ecologies for thriving in? And so that the next person that comes along that makes this interesting is Lebbeus Woods, and this slide here with experimental architecture is a drawing by Lebbeus Woods. Now, Lebbeus Woods used the platform of drawing as experiment. So he didn't actually conduct physical experiments. He used drawing as a thought experiment that could deal with variables that architecture and its existing technology simply couldn't deal with. So, for example, catastrophic natural events like earthquakes, or in this particular case, this is a response to war in architecture in Sarajevo. So my own contribution to experimental architecture is not through drawing, but actually in developing laboratory experiments and prototypes. And this is an experimental apparatus that was set up with the Cronin Lab in Glasgow. It is bringing together scientists, 3D printers, and chemists and designers around the 3D printing apparatus. And here we've got activated gels, and we also have inorganic solutions, and we're looking at versions or spatialized versions of the Liesegang ring reaction, essentially a well-established diffusion precipitation system driven by gravity, and using the body of the gel and physical configurations to try to roll and fold this sequence of diffusion precipitation events almost in an embryological way. And so this kind of experiment, you know, we've not created a building using this. So this work is considered within this domain of inquiry that we're calling experimental architecture. So it's searching in an architectural context for new ways of choreographing the production of space by growing, for example, rather than building structures. Using these new spatial techniques and design programs, we can potentially open up radical new pathways for exploration and qualitatively different kinds of practice within the field of architecture. So again, this is not a mature practice. This is really about developing prototypes, coupling them together, interrogating them as installations, you know, and potentially using this experimental platform, which I think is vital when we're thinking about highly complex, engaged material systems, you know, that we actually understand it in an immersive, physical sense before we start making large commitments to building projects. So really, this is a forum in which design and art and science and engineering converge. So my current journey, now this is the range of systems that I work with, and you may have come across them before. Some of them will know them as protocells. They're actually dynamic droplet systems. This is a droplet system that was demonstrated by video by Takashi Kugami at the Artificial Life 11 conference in 2008 at the Winchester venue. An amazing conference that was curated by Seth Bullock from the University of Southampton. And it brought together, you know, for the first time, a large contingent of biologists and people working in, let's call it computing sciences and information technologies. And what really excited me was that this droplet, which is basically benzene with an anhydride metabolism in an alkaline environment, was able to shed a structure, almost an amniotic kind of structure, without a central program. And for me, coming from a design perspective, this was very much an architectural proposition. This showed to me that something that had a kind of a distributive set of operations could produce structural solutions. And I really wanted to find out more about this. So I then started to work with Martin Hanzuk, who was then at the University of Southern Denmark and now at the University of Trento. And he introduced me to this fantastic system here. This is the Büchli system. It's over 100 years old, described in the literature in 1892 by zoologist Otto Büchli, who was obviously trying to, let's say, devitalize notions of biology. In other words, he was trying to say that biology really is a much more highly complex version of chemistry, but essentially biology shares fundamentally chemical principles. And so when he added potash, so potassium hydroxide, to a field of olive oil, he saw a droplet spreading out, a bit like this one here, which has been designed by Martin Hanzuk, stained, with a red and a blue dye. And he said that the field effects that then happened as the droplet broke down through the dynamics of surface tension, underwent what he called an amoeboid reaction. And when you have a look at this video, I mean, you'll see it happening in real time. The dish itself is about 4 centimeters across, and the highly dynamic, rather amoeboid fragments that you see are about 1 millimeter across, and that's really what I study. So you'll see the droplet spreading out, it's starting to break down, you'll see like amoeboid bodies in the middle there, and they start to move around the dish, they start to seemingly interact with the environment, and that's where my field of operation is situated. And these droplets are really about 1 millimeter in diameter. So what did I do? Well, I looked at it for the first time underneath a modern microscope in over 100 years. Hopefully I haven't advanced by 2 frames, because there's a bit of a lag between me clicking on the screen here and the video coming up. But what you're going to see next, I hope, and not skip along too, is a × 4 magnification of the Büchli system. I'll try again. Let's see if it it's just a question of time lag, or whether I'm now 3 slides advanced and it's trying to catch up with me. But I'm looking for a video that shows what happens when we dive down into this reaction that I'm showing you, the way that you'd see it in the laboratory here. Now I don't seem to, oh, there it is. So what you're looking at here in real time is the addition of the sodium hydroxide droplet. You can see that there are a set of phases. I use Stéphane Leduc's notion of the mechanism of life, where 20 years or 30 years after Otto Büchli, he again coins the term synthetic biology. He uses it to describe biological-like phenomena that have arisen from chemical reactions. And one of the structures that Leduc uses is the notion of an osmotic structure, which I'll point out in just a second, because he said that he thought that they were homologous to fungal-like structures. Now, I mean, we are really talking in a very metaphorical sense, but what I think is interesting about Leduc's engagement with these lifelike phenomena is that he does attribute life stages to them. So the first stage there, where you see almost like Matryoshka Russian dolls bursting out of each other, manifolds of chemical activity, we could think of that as a kind of birth. we can think of these now more organized forms, which are like amoeboid bodies that are very highly coupled to their environment, and I'll talk about that very shortly, as being the life phase. And you can see an osmotic structure, almost like a tail-like outgrowth of that body at the top of the screen, and how diverse those bodies are, after the birthing phase. So you've got a dissipative system. It sheds a lot of energy at the time of, let's call it, its birth. It becomes more organized because of, this massive shedding of energy and the production of solid systems. And then it gradually reaches an equilibrium state. And this is what, Leduc would probably describe as a death or a decay-like phase of the development of this rather lifelike system. And of course, it is not alive. This is purely physical chemical interactions, and yet, within this system, I think for me, when looking at notions of intelligence, you've actually got quite a direct view of how matter and information are being coupled. And I really don't want to confirm this system with, sophisticated forms of intelligence, and I will infer a definition a little later on that I feel more comfortable with than, let's say, the kinds of intelligences that are invoked in, the developmental of artificial intelligences, which tend to want to be human-like. It's my view that there are a range of intelligences, and they are appropriate to the range of material systems, to the ones that we are observing. And I think it is highly problematic to try to categorically list absolute characteristics to them. So I'm really taking an observer's, or let's say a designer's view here. So essentially the thing that's doing the operations here is a dissipative structure. And I really want to position dissipative structures as being the key to this perspective that I'm taking on embodied systems. Again, I'm trying to advance the screen here to show a picture of a tornado, and I'm just suffering a little bit of lag between my slide presentation. So, I mean, you've got there another view of dissipative structures. Yes, this is sort of tornado, and I kind of want to talk about the dissipative structure in case people haven't come across it before. So a dissipative structure was a paradoxical material entity. It was described by Ilya Prigogine. He won the Nobel Prize in Chemistry for this idea in 1977. And it's a paradoxical entity because it's both an object and it's a system. And it exists spontaneously within nature in a range of physical structures, so that on the small scale would include forms of chemical and crystal growth, and on a very, very large scale, the birth of galaxies and constellations. But I'm going to use the tornado as an example because I think it gives us a set of qualities that helps us design and engineer. Consider this as being a platform for the construction of, let's say, embodied intelligences, or even just embodied information that is dynamic and can seem to make a qualitative set of decisions that are very, very hard to be empirical about because of the diversity of them, given that they are complex structures. So a tornado, first of all, is not made by coupling objects together. It arises from an energy gradient and a material gradient that's produced by atmospheric conditions. And it arises as an irreducible whole. It is not a set of objects that are meticulously coupled together. We could take an atomistic worldview of that and say that this is the atomistic assemblage of molecules. But in terms of producing the structure, for me, this is assembled de novo as an irreducible whole, and made of this overlapping and energy and material gradients. Now, each tornado has a range of unique characteristics that make up its body. We can recognize it as being a tornado because it has this grouping of characteristics. So it's a vortex-like structure. It's associated with weather. It has a recognizable patterning that allows us to call it a tornado. But no tornadoes are exactly alike. It continually takes in matter and energy and distributes it until it reaches equilibrium. Now, as it does so, it has a field of operation that extends beyond what appears to be the central object. So we can imagine yourself as a storm chaser. You can see the object, the vortex, but you actually feel its effects way beyond the apparent boundaries of that system. So I find this is quite an interesting thing from a design perspective, that I can engage with that system at a distance from the object and potentially influence its morphology and even potentially its interactions without having to physically manipulate that object. Also, because it is an actual material structure and not a representation, it's a material phenomenon and decreases to some minimum level and seems to seed the occurrence of the next one. I don't know if I've got my next slide, which should be, okay. So, I mean, distributed structures appear in clusters. And the reason for this, I think, is because of this material phenomenology, this field effect, and the fact that they are actually made using matter, which is tightly coupled, as a product of program, environment, and process, and this confers them with a huge amount of plasticity. And for me, in terms of addressing the question or the range of principles that you're exploring in this lecture series, I think this is the point of connection, because I realise that probably most people aren't presenting chemistries as being a subject for discussion. So it's this tight coupling between program structure and process and environment, this ability to be assembled spontaneously as a whole and not as a series of parts, but also the temporality of these systems. These distributed structures are not infinitely continuous. There's a point at which the storm chaser does not feel the field's effect of the tornado, and that the tornado also collapses and succumbs to these forces of disorder or entropy, at which point they lose these amazing interesting properties. This is the point at which Leduc would say that they are no longer alive. Right, I'm having trouble advancing them. So I can see the so we've got technical issues if you've not been able to see the slides on the system here. I can see there's a video on screen, but it's not appearing to advance from my computer. So excuse me whilst we try to figure this out. Yeah, shall I just walk through? If I go through the.
Where do we need to be?
Yeah. Yeah. Okay. So it's just that it's not been forwarding from here. And because I could see it from the screen. Let's see. So if we.
Is this the correct one?
Yeah. No. We'll go forward another. So that's the tornado. This is the tornado that I was talking about. Let's see.
If you just press this.
This one should take it through. This is a set of coupled structures. You know, this is the Bootstrap system that I've been working with. And as you can see, you get clusters of bodies. There's a field effect that they're working with. They're actually able to produce material responses to their environment as a product of shedding energy and matter through their own assembly and, let's say, just physical dynamic processes. And here, this is a very interesting phenomenon. I'm talking about a range of induced effects that I can provoke in this system, whereby you know, we can precipitate mass assemblages, mass collections of some of these dissipative systems. Yeah, yeah, no, that's fine. Thank you very much. So this is you know, precipitating because of this tight coupling between program, you know, matter and environment. You know, by changing the environmental conditions. So in this case, by adding alcohol to the oil field, I can induce swarming of these droplets and create what Timothy Morton, in a cultural sense, would call a hyperbody. So, you know, the idea that, you know, a dissipative structure has a certain set of qualities about it allows me, as a designer, to actually manipulate the system in ways that create a great deal of plasticity and robustness in a range of material solutions, which are creating, I guess, a platform for production that has some interesting qualities that allow me to answer or address this question of environmentally sensitive materials that I'm looking for in an architectural context. But as I mentioned, you know, that because they are far from equilibrium at the beginning, they eventually decay towards equilibrium states, and obviously this decay is something that nature does very well. And you know, develops a set of strategies to resist through complex metabolisms. So what I'm going to talk about then really is how have I worked with these principles in design to actually propose a range of interventions that I will call design. I won't call them engineering solutions. I won't call them even formal architectures. What this you know, next series of slides is going to be about is how have I worked with the idea of the dissipative structure and its innate properties to show how we might construct them, then how we might manipulate them, and then how we might deploy them within a certain set of contexts. So to produce dissipative systems, first of all, I set up this very simple demonstrator, and I hope you can see on the screen almost like a two-tier graphic. Now, this is an installation that I did in Belgrade, whereby the lower part of the screen is made of glycerin. So what I'm doing effectively is setting up a field, setting up some physical tensions, physical and chemical tensions that will precipitate the evolution or the probability of a dissipative structure. And for me, that's the first interesting move. I'm not designing an object. I'm designing a field in which the production of an object that I desire is probable, not inevitable. By understanding the rules of my gradients, I can increase that probability to almost 100%. I would never say it was ever 100%. We get bad days. So in this particular graphic, what you see is a lower layer of glycerin, an upper layer of olive oil, And what I'm playing with is the idea of the distribution of water. Okay, so glycerin is highly hygroscopic. It loves water. It will associate with water molecules. And of course, olive oil really doesn't want to know water at all. It is not at all hygroscopic, and it will repel water. So the idea then was, could we take an indicator, in this case a very simple food coloured droplet which contains water, some oils, and create some tension within that resource, let's say, and put some rock salt within it. Rock salt contains hygroscopic impurities, and so what I'm doing really is making the glycerin work harder to get hold of that water. And you will see that there are trails, if you look carefully into the coloured spots on the screen, you will see that they have little trails. And what happens is that the water droplet sits between the glycerin and the olive oil for several seconds. It wobbles around a bit as it starts to succumb to physical and chemical forces. And then the water is literally collapsed and sucked out by the glycerin in a very quick vortical structure. And it drags down the granules of salt, which are now stained. And you can actually see how that water has been distributed into the glycerin. And all I'm doing here really is showing that we can precipitate dissipative structures so that we can build them, but we don't build them as a series of objects. We build them by creating tensions. Specifically, the site of construction is the interface. So it's not in the big fields of olive oil. It's not in the big fields of glycerin. It's actually at that interface. That's where everything happens. And so by constructing an interface, we can precipitate and build these, I guess, structures that have been caused by dissipative systems. So again, how does this actually help me? Well, obviously, the Büchli system, the one that I've been working with, is an overlapping field set. So we've got alkali and we've got olive oil, and when we overlap those, we get a different kind of dissipative reaction. It's not a typical vortex, although those shell-like structures that you may have seen at the beginning when I showed the black and white video, and I'm not sure you guys actually got to see that, and maybe at the end, if there's videos that you haven't seen, we can go through if there's time. But you'll see that there's a shell-like structure, which I think is the equivalent of a vortex in this system. But essentially, the dissipative structures that are produced that I'm interested in are the ones that are in the life phase of the dissipative field, and they take on these droplet-like activities. Now, what I'm interested in is how, instead of just looking downwards for the solutions to this, to for example, get, let's say, very engaged with the fluid dynamics, which are incredibly interesting because they're incredibly complex. I can actually just relax and say, this is a dissipative structure. It is a program that is tightly coupled to its materiality and its environment. And I'm interested in the way that it couples with other bodies in its environment to produce effects. So what I'm going to do is show you some videos that just show some interesting phenomena. I'm not going to make any huge claims about them. I'm just saying that by looking at dissipative structures, that we potentially can create, let's call them embodied intelligences, that produce effects that are strikingly lifelike. And again, I'm having trouble advancing my, there we go, right, okay, I've advanced the slide. I hope you can see on this video, it may be that you might need to darken the light in the room, because this is a black and white video, and I apologize for these because The microscope that I was working with would only take black and white, and if you don't have quite a high degree of contrast in a viewing platform, you might find some of the details difficult to see. So if you darken the room, you'll be able to see the phenomenon. So what you're looking at are forward Beachley droplets. And actually already by the time I've started to speak, you can see that one of them is undergoing quite a striking morphological transformation. So that rather cylindrical object with almost like a head was one of those spherical, like droplet-based structures only seconds ago. And we're looking at a phenomenon that I've, from a design perspective, I've colloquially called the werewolf moment. And it's a physical phenomenon that happens when there is an optimal relationship between the volume of sodium hydroxide, which is inside the droplets, just to orient you. The scale is, each of those droplets is about 1 millimeter in diameter. And the surface volume to area ratio of each of the droplets. And it's optimized so that the production of sodium oleate, the soap made by the system, is at its quickest. And there's a Marangoni effect that circulates the sodium hydroxide within the sphere, and it's actually able to produce the sodium oleate at its quickest. And as there's a circulation, the oleate crystals get swept to one end of the droplet. So it's actually polarized from the outset. There is a head and tail, there's an anterior and posterior of this droplet from the outset, owing to molecular disturbances, the inequalities within the environment. It is environmentally attributed. It isn't like in, say, embryological development, where RNA by the mother is placed at one end of the egg, let's say, according to Speymann's and Mangold's experiments. This is an environmentally attributed head and tail. But essentially the way in which the droplet starts to move is the head, and the deposits are the tail, and so they are intrinsically polarized. And as they do this, they produce a structure which then contributes to the movement of the system. So there's drag being produced. As you can see, obviously the olive oil is highly viscous. And there's actually now another droplet that is moving into the field. It's coming from your bottom right view, if you're looking at the same kind of view that I am. And there's something produced in this environment that actually recruits bodies. Again, as part of the dissipative system, as part of the production of a field of effects, and also through the consequence of diffusion. So you actually get quite a lot of recruitment into this field. I'm not exactly sure how to induce that, but it's a phenomenon that's happening because of this tight coupling between materiality, information, and environment in these bodies. And what I find quite striking is this rapid ability to change morphology and engage in, let's say, population scale behavior. Again, like the brief video I showed earlier, we can influence this event. We can speed it up by adding alcohols. So if we change surface tension in the system, we can alter the effects of this. So it's not a technology yet, but there are qualities within observing these materials that lend themselves to operationalization, that lend themselves to further technologization. And I'm just showing this same kind of event on a much greater magnification here. It's quite difficult to keep it in sharp focus. This is at about times 10 magnification on this particular slide. And I'm just showing it really to show you the degree of physical forces. So you can actually see that this is quite a vigorous disturbance that's happening within the droplet. You know, this is not just simply a quietly constructive synthetic event. That there's a great deal of turbulence that's going. You can see the way that the droplet is actually being pushed around by the molecular events in which you know, the physical and environmental systems are actually moving the interface around. So remember, it's the interface that's doing all the doing. That's where the sodium hydroxide is meeting the olive oil, and the you know, energy absorbed to produce sodium oleate is actually taking place. So I won't go all the way through this video. It produces a very similar kind of morphological event to the one that we've seen just previously at the population scale. But I just really wanted to show it at a higher resolution. I think there's something to note that the droplets don't tend to fuse in the Buchli system. And I've always found that quite surprising. I think it's got something to do, again, with the physical qualities and, you know, dynamic flow within the structure. Buchli droplets do fuse, a smaller proportion of them do, and I did manage to capture fusion a couple of times on video. Unfortunately, the camera managed to fail when I'd actually got one of them stained with fluorescent, but what you see is a fountain of, let's call it a Marangoni effect, moving from one droplet to another. So these bodies can couple, but they generally don't tend to. They generally tend to repel each other as much as they're attracted to each other. So there's a degree of cybernetic, let's call it, activity within these bodies. I mean, as you can see, that one of the bodies now is reaching this tipping point, this series of now pre-terminal events that are characterized by this, you know, hyper agitation, the production of a rapidly elongating structure, and rather erratic movements. So, I mean, at this stage, I'm just going to refer to a TED video by Alex Wisner-Gross. I mean, it's only just been posted on TED, so I'm not sure if anybody's looked at it. I'm sure that there'll be plenty of opinions as to whether or not you agree or disagree with his observations about intelligence. But essentially, he makes an interesting observation about intelligence that I think is applying it to the Buchli system in some ways. That he says that intelligence is a physical process that maximizes future freedom and resists future confinement. And so I guess I'm making this statement in, again, a context of not really wanting to over-define what we're looking at on the screen as being truly intelligent behavior, but more of in terms of this notion of morphological computing. Alex Wisner-Gross creates an equation that relates force of intelligence to the product of T, which is strength to maintain future actions, S, the diversity of future options, and and delta ST, so the change in strength with diversity of future options and time horizon. I think I've got the equation in the next slide, but if I don't, I thought I would read it out. I'm showing this particular video here because it's an example, I think, of a form of embodied intelligence that speaks of a different kind of locomotion. So essentially, we've got this program, which is sodium hydroxide meeting oleic acid to produce a soap-like structure. Now, when I'm looking at these droplets, the microscope's looking from underneath the bottom of the Petri dish. Depending on the volume of the sodium hydroxide droplet, it will mainly float just above the, a thin film of oleate. But when it starts to produce a lot of oleate, that produces enough mass and drag on the system that will drag the droplet down so that it's in contact with the glass. And so what's interesting about this video is that as the droplet, using the sodium hydroxide meeting the oleate program, is that it goes from a free-swimming droplet, which didn't have a structure attached with it just only a few seconds ago, to something that actually appears to change its locomotory qualities and drag itself across the bottom of the Petri dish. It's not quite there yet, but you can start to see the first ripples that are creating this change in quality of what appears to be the boundary of the droplet. So you can start to see ripples as the droplet is deforming now. It's got drag, it's got a larger kind of structure at the back of the system. And it doesn't like its own waste. It's really not very, it doesn't like its own waste. And that's, again, I think it's stopping molecular exchange, at the interface. So, I mean, I don't think there's anything magic about it. I think this is simply a physical chemical system. But what's interesting is the plasticity of the solutions through this highly, highly coupled body, information, and environment system, whereby now, given that it's increased its mass, the actual physical locomotion changes from something that appears to be free swimming to something that starts to move in a different way. And I'll leave that up just for a few more seconds, because it's just starting to be able to, it's gathering enough energy to reorganize its operations so that it can continue to move. But I hope you've been able to see the. I mean, that's me moving the camera there, but it's starting there again. So it's now gathered the energy again. So it's actually a different kind of locomotion, really. For me, it touching the bottom, it's now using friction as part of its embodied solution. So I think that the fact that it's able to change strategy, I'm not saying it's doing it with some overall intention in mind, but this hyperplasticity, I think, speaks to the notion of Alex Wisner-Gross's idea about maximizing future freedom and resisting future confinement. To me, that there's some kind of relationship between the way that this system begins to locomote and diversifying material outputs. So I'm going to try and move on to the next one. These are actually my favorite videos of all time. Again, they take a little while to orient yourself around. This again is the Buchley system. All of these experiments are conducted under the same conditions. They're all at 20 degrees C. They all involve 3 molar sodium hydroxide. But I cannot control at this stage whether I'm dealing with one droplet or whether I'm dealing with clusters of droplets. It really is a question of using the microscope to scan the field, the breaking up of the field that you saw at the beginning, which was the blue and the red droplet, turning into these fields of operation and dissipating into these little bodies. In this particular instance, you've got a population of Buchley droplets in the middle of the field, creating these microstructures which are around about 1 centimetre long. So this is not tiny. Each of those droplets is about 0.5 of a millimetre in diameter. And what you can see from the right here is another group of droplets that are being drawn towards whatever products are produced by the system. Now, it is significant that this is Menini Menini not extra virgin. It is Menini extra virgin olive oil, but it's not the light version, because obviously olive oil has impurities, and there's something about the impurities that I wasn't able to characterize by mass spectrometry that actually increases the dynamism of this chemical system, and I can't nail it down, but there is significance in the fact that it is not pure olive oil. So what you're seeing now is the convergence of two populations of bush leaf droplets under the same conditions, made with the same batch of olive oil, and they appear to be undergoing this kind of attractive, repulsive, let's call it almost cybernetic exchange. So at this stage, we could think of this as being, let's call it chemical cybernetics. But there's then a synchronization of the system. I guess the nearest thing I could think of a homology is, and perhaps a kind of reverse quorum sensing that we see in bacteria when a tipping point is reached and an information signal is given to recruit, it's an order to recruit bacteria towards a food source. In this particular physical system, the information seems to want to cause the droplets to repel. So the native default setting, that the majority of these droplets want to actually cluster. But there seems to be some change in program here. Again, I'm not adding anything to this particular system. This is a native property of the
sorry,
system.
Rachel?
Yes, sorry.
Sorry
yes.
to interrupt you. We're a bit short in time. So,
yeah. Okay, yes. Well, I'll wind up now then, really. I mean, this is just simply another example of this through the material effects of coupled chemical systems. Again, between two very simple interacting groups, again, this kind of phase change activity takes place. So they reach out towards each other, and then, when they're actually coupled together, they appear to undergo this phase change in operations and diversify. And what I'll finally do is just quickly run through a set of slides that then show me show just how I've used this in a design context. Let's go to some of these architectural scale projects. So, I mean, these are at a very small scale. They're at obviously the millimeter scale. Again, I'm having problems advancing the slides. Let's have a. So, I mean, maybe you'll get to see the way that the droplets fly apart, but you've just seen that. So I'll try and, yes, here we go. So the way I've used this is by scaling up, making the droplets bigger, adding waste to the droplets to slow them down. I then used the clustering system to create nests of activity within a cybernetic framework called Hylozoic Ground, which was exhibited at the Venice Architecture Biennale in 2010 as a work with architect Philip Beasley. This is a close-up of these systems. Notionally, they're absorbing carbon dioxide from the system to produce tiny microstructures that are about the size of your little fingernail in terms of the scale. The idea was then, could we scale this up to the size of a city, exploiting Venice's natural infrastructure, which are the waterways. And the idea was to design a set of droplets that would move away from the light so they wouldn't clog up the canals. And then when they were under the foundations of the city, to then create mineral structures. This is a droplet that was designed by Martin Hanzuk that shows that we can develop a lighter versus metabolism to help us achieve this. And also here, actual physical systems within the waterways in Venice, which are produced biologically. So the idea was that we would create something that was a co-construction between nature and humans. So really this speaks about an architecture now that is coupling bioprocesses, coupling material systems to produce qualitatively new kinds of experiences within the home. This is the Philips microbial home project where microbial systems are used to produce things like biogas that may help us develop a new ecology of cooking and using the kitchen environment. The first architectural scale installations of these kinds of systems have already been made, opened last week by a construction engineering company, Arup, in Hamburg. This is called the BIQ home, the intelligent building home, where algae, these little green cows that eat sunlight and carbon dioxide, are using air, carbon dioxide specifically, to create biomass that is collected, dried and burned back within the building to set energy and therefore improve environmental impacts. So really for me, the field of experimental architecture is exploring, a range of materials, a range of prototypes to try to think about what future architectures or what environmentally sensitive architectures might be, almost as kinds of nature, let's call them synthetic ecologies, and start to make the first scratches towards a material set of solutions that are more lively than traditionally used in the environment. We could probably call them, kinds of living architectures. So I'm aware of the time, so I will stop my presentation there. And I'm happy to take questions if there's time.
Well, thank you very much. So, are there any questions?
Done. Thank you for bearing with me whilst I got my bearings around the interface here. And I think this is an amazing platform. I really love the diversity of audiences. So thank you ever so much for being present. I'm going to make sure that...
Excuse me?
To these. Yes, if there's a question somewhere, I can't say who's got there.
Okay. I just have a question. Is it possible, to what extent it's possible to model the structures which you presented in mathematical way?
Yes, I've tried. Autodesk have been wonderful. So Autodesk helped me do some agent-based modeling. I must say that Autodesk are wonderful. We didn't really we created things that could wobble around a bit, but they really didn't undergo the kinds of sophisticated morphological effects that the chemical system produced. However, I will say that the best and closest model I've seen is Stefan Raffler's Smooth Life, which is a CA with floating integers. So I think thinking of the distributed structure and the fact that it also doesn't really have a firm baseline for counting has something to do with those homologies. It's something that I'd really like to delve more into. I think there is also something about the physical coupling. I think that the actual materiality of the system is producing something unique, but that doesn't mean that digital modelling has nothing to help us understand about that. I think that the closer that we can approximate the two systems, I think helps us understand this notion of intelligence and matter with even more precision than currently we're kind of being able to do. So I think there are still a lot of black boxes in the field when it comes to intelligences. Even definitions aside. I'm very interested in materiality as a way of being able to directly view what our understanding of intelligence could be, without judging what it should be.
I believe it is easier to model it qualitatively than quantitatively, right? I mean, because it's a very complex system, yes. Quite honestly. So. Yes,
it is. Yes, but in some ways, I see the chemistry as being a computer, a bit like water has been used as a form of computing, and so for me using distributed structures as a form of computing to provide solutions that are very difficult, or to provide possibilities or seeing possibilities that are very difficult to model in other ways, I think for me becomes a kind of computing platform in itself. you know, we're kind of looking at a kind of code, but not really understanding what we can apply it to right now. So I think it's got one set of applications in the sense of, you know, understanding this relationship between information and embodiment. But I think it's also there's another set of contributions it's making as a computing platform. And in some ways, I want to play with it in that sense too. But so I think it has, you know, multiple relevances.
Mm-hmm. Thank you.
Thank you.
Okay, are there any other questions? If not, then let's thank the speaker again for a great talk. Thank you very much.
Thank you, audience.
It was a pleasure to have you with us here in the Shanghai Lectures.